Okay guys, this is going to be our last video here of the semester. I just wanted to give you a brief overview of statistical thermodynamics and talk a little bit in more detail about the Boltzmann distribution. The idea of statistical thermodynamics is it provides a bridge between quantum mechanics, where you're talking about individual molecular states, and thermodynamics, where you're talking about the macroscopic state of a large system of molecules. It's based upon statistics and counting and probabilities, and so we have this idea here that allowed microscopic configurations of the system, that is, which molecules are in which particular states, are equally probable to one another. However, different individual configurations can be equivalent to each other, okay? And so what we're interested in knowing is what are the populations of the states that have that occur with the most significant total probability. So you have individual configurations, but then you can have a distribution of configurations that are all equivalent. Which distribution of configurations is most probable? And that's what the Boltzmann distribution predicts. And it also predicts that that distribution depends only upon the temperature of the system. From the Boltzmann distribution, you can construct something called the molecular partition function, which can then be used to calculate thermodynamic quantities like the internal energy, the enthalpy, the entropy, the Gibbs free energy, chemical potential, equilibrium constants. All the stuff that we talked about in Chem 450 can be derived from the partition function. Furthermore, you can use the microscopic models that we've been developing this semester, for example, the particle in a box model for translational degrees of freedom, the rigid rotor for rotational degrees of freedom, harmonic oscillator, the two-level electronic model. All of these different models can then be used to calculate the partition function, and then you can then evaluate what are the contributions of these different degrees of freedom to the thermodynamic functions. Here, the slide just discusses a little bit more about configurations and populations, distributions. And so if you have a total of n non-interacting molecules, which each have these allowed energy levels, we want to know what set of populations for the different states, for these different molecular states, will be most probable. And that is calculated from this statistical weight. You see here it's the n factorial, where n is the number of molecules that you have, divided by the product of the factorials of all of the populations. And so this is a famous problem in statistics, and the Atkins describes how this statistical weight is conceptually arrived at. I'll leave that for your reading. But anyway, for a given set of populations, that is, how many molecules are in the ground state, how many molecules are in the first excited state, etc., you can calculate the statistical weight of that distribution. Now, the set of populations, or the set of the individual configurations corresponding to a given set of populations, fluctuates with time. That is, the system bounces back and forth between different configurations. But there is one particular set of populations for which has a greater probability of occurring than any other, especially when the number of molecules is very large. And that's what we call the equilibrium state of the system. So the question is, which set of populations corresponds to the equilibrium thermodynamic state? This brief illustration just reviews how to calculate the statistical weight. It's not that hard to do. You can use Mathematica to calculate these types of quantities, and I would imagine you'd have to do something like this in the problems. So you've got n equals 20 in this formula. You have these set of populations, and so you take 20 factorial and divide it by the product of these numbers, their factorials, and you'll get very large numbers for the number of equivalent configurations for a given number of objects and populations. Here, this is the idea of maximizing the statistical weight for a given set of n values. So this is a calculus problem. What are the n values for which this quantity, for which the natural log of w is maximized? And so you take the derivative of the quantity that you want to maximize and set it equal to 0. However, there's a couple of important constraints in our system. For example, this is the formula for calculating the energy of the system. The energy is constant. And so this is a statistical weight. You take the energy of each state, multiply it by the number of molecules in that state, add that up over all states, and that gives you the total energy. That's one constraint. Another constraint is that the number of molecules is fixed. So the sum of all of the populations of the different states needs to add up to the total number of molecules. That's the second constraint. You need to take these constraints into account when you maximize the natural log of the weight. And so that's performed using the method of Lagrange multipliers, where you take the equation that you want to maximize, and then you add to it the constraints multiplied by parameters. And that's illustrated here in this equation. Okay, so this is the set of equations that you need to solve for the values of n that will have the largest statistical weight. Because we're working with independent populations, we assume that each population is independent of one another. We can basically solve for the expression in brackets set equal to 0 for each one independently. And after some calculus, which involves manipulating this partial derivative, you arrive at an expression like this, which is easy to rearrange. And you get this expression here, which is essentially the Boltzmann distribution. Using the population constraint, you can evaluate e to the alpha in terms of the betas. This denominator here is what is called the partition function of the system. And so the final form for the Boltzmann distribution is articulated here. The population of the ith state relative to the total number of molecules in your system is given by this Boltzmann factor in the numerator, this e to the minus beta times the energy of the state, divided by the partition function q, where q is a sum over all of the Boltzmann factors for each of the states. Although we can't prove this in this section here, you can show with some additional manipulations that beta is equal to 1 over k times T, where T is the temperature of the system. And this shows that the most probable distribution, the Boltzmann distribution, depends only upon, the only parameter it depends upon is the temperature of the system. So just to give you one final point here, the Boltzmann distribution allows you to predict the probabilities or the populations of different microscopic states at a given temperature. In this example, you're considering a molecule that has two different molecular conformations, so two different geometries, and they differ by 5 kilojoules per mole, which at the molecule level is 8.3 times 10 to the minus 21 joules. They want us to calculate the fraction of molecules that have this higher energy at 20 degrees Celsius. So you need to calculate the Boltzmann population for the first state. We'll assume that 0 refers to the lower energy state, and we'll take its energy to be 0. So this term will just be 1. And then we plug in e to the minus this energy divided by kT, where k is Boltzmann's constant. And we need to convert the temperature to units of Kelvin. We do that, that gives us the partition function, 1.12. And then we take the same term here, divide it by the partition function, and we get a fraction of 0.11. This tells us that the fraction of molecules in that higher energy conformer is about 11% at 20 degrees Celsius. And if you were to increase the temperature, you would find this fraction of molecules in the higher energy conformation would increase. If you were to lower the temperature, you would find it would decrease. These two formulas are used to calculate the relative population between two states. So state I versus state J. What's the relative amount in state I versus state J? You can use the Boltzmann distribution to calculate that ratio. Here it depends upon the energy difference between them and the temperature. And so for a fixed temperature, with you look at the difference in energy, and the larger the energy difference, the less molecules you will have in the state I. The smaller the energy difference between them, the higher the population of state I relative to state J. You might be interested more in terms of energy levels rather than individual states, and the difference here being that different energy states can be degenerate. That is, they can have the same energy. So you can modify this expression here to include the degeneracies of the various energy levels, and that's another way of using the Boltzmann distribution. Both ways are illustrated in this problem here. You're being asked to calculate the relative populations of the J equals 1 and J equals 0 rotational energy levels. Here's the formula for the energy levels for the rigid rotor. And over here is the degeneracy of the different levels, right? So you have two quantum numbers, J and M sub J. The energy depends only on J. So states with the same J value but different M sub J values are degenerate. And here's the degeneracy. For every value of J, you have 2J plus 1 equivalent energies. So you can either calculate the relative populations between two states, or if you are interested in the relative population between two energy levels, you need to take into account the degeneracy of the two energy levels before you do this calculation. So you use your rigid rotor model to calculate the energy levels. Okay, you'll find that it's something related to the rotational constant, and then you calculate this quantity, and it gives you a ratio of 2.7. This tells us that at 25 degrees Celsius, you're going to have 2.7 times more molecules in the J equals 1 energy level than you will in the J equals 0 energy level. Well, the rest of the chapter basically goes through the details, the mathematical details of taking that molecular partition function and expressing it in terms of the different degrees of freedom within your molecules. So you can use the particle in a box model, rigid rotor model, harmonic oscillator model, etc., to calculate the molecular partition function. And then there's mathematical procedures for taking the molecular partition function and deriving the expressions for the internal energy, the entropy, the enthalpy, the Gibbs energy, all of the thermodynamic quantities that we studied last semester. It's a bit involved, and we don't really have enough time left in the semester to go through those details. And so we're just going to go ahead and omit them here. Please just focus your effort on this chapter on that first topic involving the Boltzmann distribution. I want you to make sure that you can use this formula here together with these ancillary formulas. So you need to be able to use the Boltzmann distribution to do little calculations like this one. And then you should also be able to use the Boltzmann distribution to calculate relative populations, both for states and for energy levels, just like this problem here. So expect a problem like this one and or like this one on the exam 3. Okay, so with that, I'm going to go ahead and stop this video.